All right, the first concept is triangle sum. Okay, so if I wanted to demonstrate triangle sum, what I can do is I can just measure each of these angles. Okay, and then test to see what is the sum of these angles if I add them together using the dynamic calculator. I get 180, and again, it doesn't matter where I move these, that total sum of the angles is always going to be 180. So there's triangle sum. If I wanted to verify the relationship between the exterior angle of a triangle, what I'll do is I'll extend one of my sides out, place a point, call it D. Okay, and so if I measure the exterior angle, and then compare it to the sum of the remote interior angles, so A and B. So again, if I go to my calculator and add A and B together, what I should see is that this measure is exactly the same. No matter what I move this to, the sum of A and B is always going to equal that exterior angle BCD. And I see that's true. All right. The next concept that we talked about was the comparison between the sides and angles of a triangle. So here, if I take my measures of AB, BC, and CA, and I find those lengths, and then I put them opposite the angle. So angle B is opposite CA, angle A is opposite BC, and angle C is opposite AB. So if I look at these, the way that they're lined up is my longest side opposite my greatest angle. Yeah, is my smallest side opposite my smallest angle. Yeah, and again, no matter where I move these, it still remains true. So my largest angle, longest side, smallest angle, smallest side, middle angle, middle side. Okay, so no matter where I move those, that relationship between the comparison of angle measures and side lengths still will hold true. Okay. All right, what if we took the following? Okay, so let's say we take these three measures here to see if they can form a triangle. Okay, and we'll stick with, let's just call e.g. the longest side here, and let's compare the sum of the other two sides. So if I add these other two sides together, okay, what needs to happen is the sum of these two sides needs to be greater than this third side in order to form a triangle. Well, we can see right here that until the point where that works, there's no way that we can enclose a space. And it's probably even easier to illustrate it with actual circles. Okay, until these circles intersect one another, we're not going to enclose a space. We won't have a triangle. So at this point, finally, they intersect. And we see that the sum of the two smaller sides is now greater than the longest side, and so we enclose a space. If we were to find what these are equal to when they're equal to each other, it's still just a segment with a point on it. So it doesn't enclose a space until we get to the point where, again, one of these circles points falls or intersects on the other one, that we are able to have our enclosed space and form a triangle. Okay, so that's triangle inequality. The sum of the two smaller sides always has to be greater than the longest side. All right, next, base angles of an isosceles triangle. If you're working to create an isosceles triangle, doing it by hand is going to have two problems. Okay. One problem is trying to match them up. You might get to the point where it happens, okay, but it's not dynamically locked in place. Okay, meaning if I tried to move these, I lose my relationship that it's isosceles. Okay, so there's another way that you can approach this. Anybody have any ideas on how we can guarantee that we create an isosceles triangle on a sketchpad drawing? Jake?
Could you make like a line and then copy it?
Okay, so copying a line, again, you can do that. The fact that they might not be dynamically tied necessarily, or they might not be connected to one another, but it's going to kind of be based on that idea. Andrew?
Could you use like a circle?
Yeah, so the easiest thing to do is just use a circle, draw two radii. What do you know about the radii of a circle? They're always going to be equal, right? So if you used a circle and then just hide the reference, then you can make an obtuse, acute, like no matter what, you're always going to get measures that represent your two equal sides. No matter where you put it, no matter how you arrange, you're always going to have an isosceles triangle, and it'll always be dynamically tied and locked in place. So if you are going to be doing an isosceles triangle, you should use a circle to help generate it. Okay, and then finally, the last concept is the triangle midsegment. And so if we were to pick two sides of our triangle, find the midpoints, and then connect those midpoints, we can now test. Here's the measures of the lengths. Okay, and we expect to see that the midsegment is 1/2 the third side. So if I click on the third side, divide by 2, what I should see is no matter where this is drawn, the third side cut in half is always going to equal that midsegment, which it does. Okay, the other concept is that, or the property is that the midsegment is parallel to that third side. So if I select the third side and one of the midpoints, construct a parallel, you will see that that midsegment lies on the parallel.